You got it? All right. I will begin. Dear Father, we thank you for this day, and I thank you for the students. Just ask you to bless our work today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. Okay, so this is lecture 23 on prime and maximal ideals. Prime and maximal ideals. So I just skipped a couple of examples at the end of lecture 22. I would encourage you to read those. I actually have explicit factor rings and their Cayley tables, both additively and multiplicatively. You should look at those. All right, there's some examples. They are useful. But we must go on. So, definition. Let R be a commutative ring. What's that mean? What's the commutative mean? Does that refer to the addition or the multiplication?
Multiplication.
Yeah, multiplication. The addition is always abelian for a ring, right? So commutative ring and a proper ideal. Remember, our commutative rings have unity, right? There's a 1 in there. Then here's what we say. Number 1, A is a prime ideal. A prime ideal if AB in R and AB in A implies A is in A or B is in A. Now, what I just said in English kind of lets us down. Because I said A and B, well, A and B in R, like separately as elements, right? But I'm supposing that the product of A and B is in A. Okay, that's the condition. And if that condition is met, then we have the implication that either A is in A or B is in A. This is prime. A prime ideal has this property. 2, A is a maximal ideal. It's a maximal ideal of R. I missed a couple words that are probably important. Prime ideal of R here. All right. So A is a maximal ideal of R if any ideal B of R containing A, right? So with A subset of B, a subset of R, has 2 possibilities. What is the case if it's maximal? Either what? B equals to A? Or, what's the other possibility? B equals R. So if you have an ideal which contains a maximal ideal, then that ideal is either the same ideal again, or it's the whole ring. Maximal ideal. Now the terminology of prime naturally ties to like Euclid's lemma, right? Remember how this goes? Do you guys remember? If a prime divides A and B, what can we say? Either the prime divides A, or what? The prime divides B. I'm remembering this as Euclid's lemma. Is that right? I heard a yes? Okay, well, good. I mean, I don't want to give credit where credit isn't due, you know? I mean, if this is like Aristotle's lemma or something, I need to know. Oh, wait a minute. Aristotle didn't really do anything, did he? No. This is stuff about faster stuff heavier stuff falling faster. Wrong. Right? I mean, what's his legacy? Incorrect physics? Big deal. This Aristotle guy. Sorry. I was in an argument, somewhat partially serious argument with a student the other day about my opinion that Archimedes is really more impressive than Aristotle. But anyway. Okay, so this is the motivation behind the definition of prime ideal. And in fact, a good example of that is, remember we've proved that any natural number times z is an ideal. And in fact, if you take the natural number to be a prime, you know, think about that, then if AB is an element of PZ, what's that say? That says that AB is equal to what? PK. Well, more to the point, AB divides what? So this implies, would you say something? I mean, we're back to Euclid's lemma again. So either P divides A or P divides B by Euclid's lemma. And so if P divides A, this means what? This means that A is equal to Pn. P divides B, this means B is equal to, you know, PM. In either case, we either have A as an element of PZ or B as an element of PZ. All right. Let me give you an example to give you at least some sense of what are maximal ideals. And also to do something I haven't done enough of this semester, which is draw a lattice of subgroups. So here we'll start with Z36. All right. And so we have the ideal generated by 2. We've got the principal ideal generated by 3. Then below 2 we have a 4. And we also have 6. Below 3 is also 6. Below 3 is 9. And let's see here, down here I've got 12. And so what I'm drawing right now is a subgroup diagram, right? We could look at this as the lattice of subgroups of the additive group Z36, right? So now, all of these are principal ideals, which we proved last time are ideals. Like what is, just to be specific here, what does this 2 mean? This means, if you want me to get all technical and stuff, this is 2, the 36 class of 2, times an arbitrary x class of 36, such that, you know, this is in Z36. I mean, there's the belly of the beast, so to speak. Now, I prefer not to write these sorts of things, right? So instead of writing this, I would typically just write 2x, such that, you know, x is an element of Z36, which is what? 0, 2, 4, 6, 8, 10. We could be here a while. 34. should have picked a bigger generator, right? It's much easier to do for 9. Like, what's 9? You got your 0, you got your 9, you got your 18, 27, and then that's it. All right, anyway, just so we're all on the same page about what these brackets mean. These are subgroups of Z36. Which of these subgroups are maximal? So the subgroups are also ideals, right? I mean, why are they ideals? Well, they're principal ideals, right? So we proved something generated by one element is an ideal. So they're ideals, and they're all proper, right? None of them is Z36, so we can ask the question, whether or not they're maximal. So which ones of these are maximal ideals in Z36? Let me ask a slightly different question. Why is 9 not a maximal ideal? Since what? Yeah, since 9 it's a subset or a subgroup, if you like, of 3, right? And 3 is not equal to Z36. And 9 is not equal to 3, right? So neither of the terms or conditions for the ideal containing 9 work out for us. They're not equal, and it's not the whole thing, so 9 is not maximal. But it's really easy to see on the subgroup lattice which ones are maximal. You just go to the top, right? So the maximal ones here are exactly this and that. These are maximal ideals in Z36. All right? Now, you could choose a smaller universe, all right? You could look at which ideals are maximal ideals in 3. So if we look at our ring being this one, suppose the ring is 3. What are the maximal ideals of 3? The principal ideal generated by 3. Yeah, 6 and 9 are those. So these are, in fact, maximal ideals of 3. So something might be maximal with respect to one context, but not with respect to another, right? I mean, all right. Let's look at an example which is a little bit fussier. We can, in fact, show that the ideal that I ended last class by looking at we can look at the A equals to x squared plus 1. This is a proper ideal of the real polynomial ring. In fact, we can argue that this is maximal. All right, let's do it. All right, so what would it mean for this? Oh, I don't want to put A equal to that. I'm sorry. I did not call this A. Oh, this is unfortunate. So the usage of A in this example is contrary to the usage of A in the definition. All right? Now, if I had an editor, this kind of thing might not happen, right? But I don't. So let's call well, am I wrong? This is fine, actually. Let B be an ideal of R of x such that, so I'm just not writing what's in my notes, I'm writing what's logical, if that's okay. I mean, the notes are not illogical, they're just not ideal. Yeah. 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 Sorry. Oops. So let B be an ideal which contains A, where A is the ideal generated by x squared plus 1, all right? Oh, man. All right, bear with me. I have to translate this example. I've got A throughout it, and every one of these A's means B. All right, that's fine. We can think through it. Let's think through it. So, what do we want to do? We want to say, suppose, so suppose that f of x is in B, but f of x is not an element of x squared plus 1. The principal ideal generated by x squared plus 1. All right? Then by division of polynomials, there exists q of x and r of x for which the following. By division algorithm for polynomials with real coefficients, there exist r of x and q of x such that what? F of x is equal to x squared plus 1 times q of x plus r of x, where r of x has what form? So the rule is that it has degree less than the divisor, x squared plus 1, right? Which an arbitrary remainder looks like what? Something like, what letters did I use here? Little a and little b. So a, little ax plus b. Any other letters than a and b there would have been a better choice. All right? But anyway, there it is. All right. So, question. I say r of x is not equal to 0. How do why can't r of x be 0? I mean, the division algorithm doesn't say r of x can't be 0. If r of x was 0, what would it say? It'd say nope. In other words, I'm going to say, notice r of x equals to 0 is no allowed. Since what? Yeah, that would say, exactly, it would say f of x is equal to x squared plus 1 times q of x, which would say what? That would say that f of x is an element of this guy, right? Because it would make f of x a polynomial multiple of x squared plus 1, which is to say it's in the ideal generated by x squared plus 1, which is forbidden. So that can't be the case. Therefore, r of x is not equal to 0, which means what? At least one of a and b is non-zero, right? Agree? I think we can agree on that. And now for some math magic. Ah! I lost the cap. Oh well. So check this out. Now there's some rather sneaky calculation. Some rather sneaky calculation that's about to happen here. Here it is. Ax plus b is equal to, look at this, f of x, okay fine, I guess it's not that sneaky, f of x minus q of x times x squared plus 1. Okay fine, I guess it's not that sneaky. Basically, we just solved this equation up here for r of x, right? That's all we did. I'm overselling the sneakiness of this. But what can you say about this object right here? Let's break it down. You know, like yo gabba gabba. Let's see here. So this is this is an x squared plus 1. Bless you. And so I don't. Oh, it's not x. I wanted. Okay, it's not x squared plus 1 I'm interested in. It's this now. Okay, so this. All right. I mean, this is in B. Why is this in B? Oh, yeah. Thank you guys. You guys got it. It's because it's in here, and that's a subset of B, right? So both f of x and q of x times x squared plus 1 are both in the ideal B, which means that their difference is in B. So this is altogether an element of B. So ax plus b is in the ideal B, right? Moreover, you can look at a squared x squared minus b squared, which is equal to ax plus b times ax minus b, right? This is an element of what? So we just proved that this is in B, right? Right? Now this is in R of x. But B is an ideal, right? So we have Uber closure, which means that that product is again in B, because B is an ideal. All right. So then I have, therefore, as a squared times x squared plus 1 is where? That's also in B, right? What do I get then? I get that 0 is not equal to a squared plus b squared. Why is that? Right, because at least one of them is non-zero. And that can be rewritten as a squared x squared plus a squared, parentheses, minus a squared x squared minus b squared, right? Which, of course, is equal to, well, the point of that is that this is an element of, you guessed it, B, right? Do you understand this? There's a multiplying out that happened right there. This is a squared x squared plus a squared. That's what's written down there. So we've got difference of things is in B again. All right, so what have we got? What have we shown? So that gives us that, 1 over a squared plus b squared times a squared plus b squared equals to 1 is in B. Therefore what? What did we say last time? If 1 is in the ideal, what did it force? Remember, if the multiplicative identity is in the ideal, that means that it's the whole thing. So this says that B is just equal to R of X. And that proves that this ideal is maximal. Now, the thing I'd like you to glean from this discussion is that this method of argument is kind of difficult, right? I mean, it actually requires a lot of kind of persistence and a little bit of sneakiness. I don't think I came up with this. Yes, sir. Uh-oh.
I'm sorry, I can't see through the computer screen.
You can't see through the computer screen.
I think it has lead in it, so.
If it didn't have lead in it, wait a minute. Can Superman see through lead, right? No? Oh.
I think it was lead.
And lead is he can't, because he's got the X-ray eyes. Yeah. That's a good point. Is that better? Okay.
Thank you.
All right. There we go. Apparently A is a maximal ideal. So before I erase all these examples, I'd like to point something out to you. R of X mod X squared plus 1, we argued last time is isomorphic to the complex numbers. By the way, to make that argument at the end of last class more careful, you know what would have helped us? The division algorithm. The division algorithm clearly shows you that you can choose the representative just to be the linear term. That's what we should have used. That was missing from last lecture. How about this though, while I'm at it? How about these maximal ideals? What's Z36 mod this maximal ideal? What's that look like? I mean, this is 2. What's the coset? The only coset here is 1 plus 2, yeah? You've got the coset of evens, the coset of odds. So what's that? This is isomorphic to what? Z2, right? In contrast that to Z36 mod 4. If you look at this, I meant mod 9, sorry. If you look at that, you'd have 9 cosets. This one plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. Those are distinct cosets. And if you look at it, it fills out all of Z36. Those are your 9 cosets. In other words, you could prove that this is in fact isomorphic to Z9 for what it's worth. But what's the difference between like Z9 and Z2 and the complex numbers? Which of these things is not like the other? Which of these things does not belong? The answer is 9, because Z9 is not a field. It's not an integral domain, in fact, right? 3 times 3 is 0, but 3 is non-zero. Z2 is a field. By the way, if we took Z36 mod this, we'd have something isomorphic to Z3. Z3 is a field. Z mod any prime is a field, right? The complex numbers are a field. So maybe you start to believe that if we take a ring and we mod by a maximal ideal, we should get a field. And maybe it's an if and only if, because we see what happens when it's not a maximal ideal. We didn't get a field. That's not a proof, right? We're going to prove it. All right, so let's get on with it. Hopefully I have actually left myself time to say these things carefully. All right, so theorem 4.3.6, the next big event in here. The next two theorems definitely fall into the category of theorems that I have asked for the proof of on tests before. And or half of the proof on test before. And also, in a more happy note, there are a lot of times things that a good portion of the students actually give me a halfway decent proof for. So, and some others don't, but anyway, theorem. R be a commutative ring with ideal, and I'll just get straight to it. R mod A, 4.3.6 is what I want. R mod A is integral domain. What's an integral domain? Yeah, no zero divisors. R mod A is an integral domain if and only if A is prime. All right. Here's the proof. Suppose R is a ring with ideal A. Commutative ring, of course. Commutative ring with ideal A. And the ideal, I think that ideal should be, well, I think we want it to be a proper ideal. Well, let's just say A not equal to R, okay? And let's see here. What's my next move? Suppose, further, that R mod A is an integral domain. What's our job now? Yeah, we're working on this part of the proof. You said what? Show it's prime? So how do we show something's prime? So we should be clear. Now, you guys have a kind of bad habit, a lot of you, of doing the calculation without ever saying cleanly at the start what you're, like framing what you're doing, right? So we need to start by saying, let A and B be where? In A, right? And what's that? No, in the ideal A. Well, I mean, yeah. I'm sorry, I forgot this part. But the more interesting part is that, and I've done it wrong. Goodness gracious. Sadness. Thank you. Infinite sadness. All right, AB is an A. Ugh, idiot. Me, not you. Let's see here. All right, so then, A is equal to AB plus AY, because AB is an A, property of cosets, right? And that is equal to, by the way, A plus A times B plus A, right? Aha! But what is the 0 in the factor ring? This is 0 in R mod A, right? And so what you're looking at here is a product of things, of elements in R mod A, right? And if we have a product of things in R mod A which is equal to 0, since R mod A is a integral domain, what's that say? Either A plus A is equal to A, or B plus A is equal to A, since R mod A has no 0 divisors, right? But what does that mean? Oh, I think we're in business, right? Because, again, by properties of cosets, remember A plus A is equal to A if and only if A is an A. And b plus a is equal to a if and only if b is an a, right? So this gives me that a is an a or b is an a. So we've just shown the implication. If we take a pair of elements in the ring whose product is in the ideal, then either A is in the ideal or B is in the ideal. And that's the definition of prime ideal, right? A and B, product in A implies either A is an A or B is an A. Therefore, A is prime. I think to be fussy, I'm not sure my notes make it clear that A has to be a proper ideal. I think I might be missing a word there. All right, let's go the other direction. What's the other direction going to look like? Suppose what? Suppose A is prime, right? And consider the zero divisor equation, right? Consider A plus A times B plus A equals to A again, right? To show that there are no zero divisors, we need to show what? Either A plus A is 0 or B plus A is 0, which is logically equivalent to saying either A is an A or B is an A. But this implies what? This implies that AB plus A is equal to A, which implies that AB is in A, right? And I guess to be more clear, in order to write this, what's a precondition of in writing such a thing? I really should have had in here AB in the ring, right? Admittedly, it wouldn't really make much sense to write A plus A and B plus A unless A and B are in the ring anyway. But just, to be fussy. We could all afford to be more fussy. So AB is an A, but then A is what? A is prime, which implies what? A is an A, or B is an A, since A is prime. Thus, A plus A equals to A, or B plus A equals to A, and it follows that R mod A is integral domain. Because it has no zero divisors, right? I'm going to work on this board over here. I'd just like you to remember how horrible this is. Etch it into your mind how horrible this is, because we're about to replace this with a theorem which says to decide the maximality of an ideal, all we need to do is look at its quotient. If that quotient's a field, it's maximal. That's pretty nice, because it wasn't too hard to see that R mod this ideal was the field. And by the theorem, it follows that this is maximal. Theorem I'm about to prove. If I was smarter, I'll go back to the definition and switch the role of A and B back here. Then my example doesn't need to be changed as much. Just thinking. All right, theorem. Sorry. I'll stop being an idiot as soon as I stop being an idiot. Theorem. 4.3.7. R a commutative ring with unity, A an ideal of R mod A field, if and only if A is maximal. All right, so the preconditions here I'll write in the proof. Let R be commutative ring with A an ideal. All right. This is the quotient ring. Yeah, oh, I already wrote that already. Let's get into it. Come on. Here we go. All right, so consider an ideal B of R for which A is contained in B, which is of course contained in R, with A not equal to B. All right? And I've neglected a very, very important little sentence, which is what? Assume R mod A is a field. Without that sentence, this proof would lose about 20% of the credit, maybe more, depending on how crazy the stuff I say is afterwards. I don't know. All right, now we're good. Assume R mod A is a field. Consider an ideal which contains A, but it's not equal to A. What do we need to show? What do we need to show about B? We need to show B, what's that? B has to be equal to R. If we can show B equals to R, logically, we have shown that A is maximal. All right. So now this one requires a little bit of, this, if you really get to it, this is the friendlier of the test questions, because this does not really require any kind of construction or anything especially special, right? This is just definitions and logic. There's no, oh, here, construct this set and do something silly with it. Well, here, there's something like that. Here it goes. All right, where was I? I guess first I need to earn the right to construct the set. So what's this say? There exists X in B such that what? X is not an element of A, right? Hence, X plus A is not equal to A, right? So what this means is that X plus A is a non-zero element in R mod A. And since R mod A is a field with unity 1 plus A, we have the existence of Y plus A, for which it's the multiplicative inverse of this. So let me recap that. Note, X plus A not equal to A implies that X plus A is non-zero in R mod A field with unity what? What's the unity in the field? It's 1 plus A. 1 plus A serves as the multiplicative identity in the quotient ring. Therefore, there exists Y plus A in the quotient such that what? Such that X plus A times Y plus A is equal to 1 plus A. Why is that? Sorry, the part I was talking about, the sneaky part, I jumped ahead. That was the later part of the proof, my my eyes jumped over this paragraph. Look, so this is the multiplicative inverse of that. What's this also say? This says that xy plus a is equal to 1 plus a, which implies that 1 minus xy is an element of a. Right? But what do we know about x? It's not in there, but it's an element of b, right? X is an element of b. And what else? What about xy? Xy is an element of b, right? Which is an ideal, right? So it's got the Uber closure. So anything in b times something else is again in b because it's an ideal, right? And also we have that a is a subset of b, right? It's given. So what? 1 minus xy is an element of b. Does that make sense? We've got oh, right. Since a is a subset of b, right? We've got that 1 minus xy is in b. And I've got that xy is in b. Then what's next? Therefore, how about xy plus 1 minus xy? What's that give us? That gives us 1 is an element of b. Game over, right? Hence, x, which is equal to x times 1, is an element of b for all x in the ring. B is the ring. So we've shown maximality. Once we show 1 is in the ideal, that shows it's the whole thing. So it's not just a nuance of the construction of ideal or subring that we started with, like making, it's not just a nuance of the construction of ideal. It's actually kind of so important that we did not assume 1 is in the ideal. You see, 1 being in the ideal makes something really special happen. And we see it in proofs, right? We've seen it. Now, what's the other direction of this proof here? So we just proved field implies maximal. The other direction, right? The other direction would be to assume a maximal assume a is maximal, and then what you do is you again use that x which is in b but not in a, and you consider we have x plus a not equal to a again, all right, and we construct b equal to xr plus a such that r is in r and a is in a. And then what I say in the notes here is that I leave it to the reader to show that b is in fact an ideal, and you can work out that a is a subset of b, and then by maximality, this b has to be the whole ring, right? But if that's the whole ring, then you're able to use that to show that, in fact, the ring has to be a field. So we don't have time in class today. What I'm going to do is, for those of you who come to the review session Friday, I'll cover it in there. The rest of you want to watch it, you can. It's going to take us about 10 minutes to do this carefully. I don't want to rush it here. Do you guys have any questions about this material? the last example in this section is kind of an important example. Oftentimes, like a true-false possible question might be asked on the back of this question. In this example, we have an integral domain, and for an integral domain, a maximal ideal must be a prime ideal in view of these two theorems. On the other hand, I said we can exhibit a ideal which is prime but not maximal. And so I look at the ideal generated by x and 2, and I give arguments that that is a prime ideal, which is, well, it allows me to show that the ideal generated by x in the integers is prime but not maximal. So again, I probably should talk about that in the review session, or maybe next class, depending how things go. So I'll shut up. See you guys Friday.